In section 2.4, we'll talk about using statistical graphs to organize and present data. We can see how data is divided among different categories, or we can see how data changes over time. So basically, we're just going to talk about different types of statistical graphs that are used. The first is a frequency polygon. A frequency polygon is pretty much the same as a frequency histogram, which we did in the last section. Instead of using rectangles to show the relative height, or excuse me, to show the frequency of each class, we just plot points and then connect the points with line segments. This first number on the horizontal axis would be the class of pulse rates that has 64.5 as its midpoint. I think that class went from 60 to 69, women who have pulse rates between 60 and 69, and there were about 12 women who had that pulse rate. So for a frequency histogram, we would have drawn a rectangle that high. For a frequency polygon, we just plot that point and then draw a line segment to it. We can read the frequency in each of these classes by looking at the corresponding point. It looks like the class whose midpoint was 94.5, that would have been the women who had pulse rates between 90 and 95, 90 and 99. It looks like there were maybe only about um, one or two women who had pulse rates in that class. So that's how you read a frequency polygon. And a relative frequency polygon is like a relative frequency histogram. Rather than giving the frequencies in each class, it just gives the relative frequencies in each class. That's the frequency changed to a percent of the total. It looks like for the class whose midpoint was 64.5, that would be pulse rates between 60 and 69. About 42% of men had pulse rates in that class, and about 30% of women had pulse rates in that class. So relative frequency polygon pretty much gives you the same information as a relative frequency histogram. An ogive would give a picture of a cumulative frequency distribution. Remember, for cumulative frequency distributions, they don't show how many people fall in this class, they show how many people fall below this class. So when I look at this point that has dotted lines here, that would say for the class whose midpoint is 79.5, about 25, 26 people had pulse rates below that, and about 35, maybe 38% of people had pulse rates below the class whose midpoint was 89.5. So an ogive is always going to be increasing because you're always adding up the frequency of the next class. A dot plot consists of data which is stacked along a stack of values, a scale of values. Dots represent equal values that are stacked. So this is the same information, the data from the pulse rates of females. If I was going through that original data, every time I came across a woman who had a pulse rate of 60, I would put a dot above that 60. So it looks like there were 3 women who had pulse rates of 60. There were 4 women who had pulse rates, maybe that's about 64. Looks like there were more women who had pulse rates of about 72 than any other pulse rate. And we'll talk about these guys later, but those pulse rates are pretty unusual. They're far away from all the other pulse rates. It looks like I had one woman whose pulse was about 96, one whose pulse was about 104. And that's still not terribly far away from these others. But this woman who had a pulse rate of 124, she may need to call a doctor, call 911 right away. Then we have stem and leaf plots. I use these sometimes when I'm trying to see how a set of test scores are spread out in my classes. Here, this is the pulse rates of females again, and all of the pulse rates were either in the 60s, 70s, 80s, 90s, 100s, 110s, or 120s. So I would call these first digit or two the stems, and then um, this right hand column gives me the digit that was in the ones place for each of the pulse rates. Stem and leaf plot is one of the only graphs that you can see all of the original data. I can see that I had three people, three women whose pulse rate was 60. That would be 60, this would be 60, this would be 60. I had four whose pulse rate was 64, and I had five whose pulse rate was 68. So there's all the original data for women who had pulse rates in the 60s, and then I could list the data for women who had pulse rates in the 70s and 80s. And then here's the lady who had a pulse rate of 124. If I was doing this for test scores, my stems would probably be from 1 to 10, representing scores that were in the ones to scores that were in 100. And then the last digit of the score would be the leaves. And so if I had somebody score, say, a 62 beside the stem of 60, I'd put the leaf of 62. A bar graph is a little bit different than a histogram in that it shows qualitative data rather than quantitative data. It gives data that is in categories. The categories here are, it's hard to read that, but it looks like decades maybe. I can't even read those years, they're so small. But we're comparing the median income for males and females from the years 1950 to 2000. And this would be called a double bar graph because we're actually drawing two bar graphs on one chart. I can see that, well, I can hardly see it all. That must be 1950, 2000, 2050. So in 2050, it looks like the median income for males was about maybe three times as high as the median income for females. And then in the year 2000, men are no longer making three times as much as women. They're now making a little bit over, well, a little bit less than twice what women make. So the women median salaries are gaining on the men's. A Pareto chart is just a bar graph that is put in descending order. This represents the responses of 12,500 people who were asked what contributes most to their happiness. And I should have copied these charts larger for myself, but it looks like family and friends was the number one response. And it looks like about 65% of that 12,500 said their family and friends are their greatest source of happiness. Over here, the lowest source of happiness is derived from sports. So a Pareto chart is just this bar chart with the categories arranged in descending order. The statistical graph you're probably most familiar with is a pie chart. It gives a good visual image of what portion of the population falls into each category. This is the 12,500 people surveyed and asked, what's the greatest source of your happiness? And here again, we see that family and partner was the answer given by 65% of those surveyed, over half of those surveyed. And the smallest slice of that pie was sports. Only 3% of people said sports gave them more happiness than anything else. Now, in the homework, you have to ask some questions to answer some questions to interpret a pie chart. They're similar to these. First, of the 12,500 people surveyed, how many people gave sports or leisure as their greatest source of happiness? Well, 3 people said sports was their greatest source of happiness. Um, that looks like 8% of people said leisure was their greatest source of happiness. So that's 11% total said either sports or leisure was their greatest source of happiness. But we weren't asked what percent, we were asked how many people gave sports or leisure as their greatest source of happiness. So we need to find 11% of 12,500. And remember, to find that, we just multiply 0.11 times 12,500. 0.11 times 12,500 is 1,375. Now, it just happens to turn out in this problem that that ends up being a whole number. But certainly, if I had multiplied something else times 12,500, we are very likely not to have gotten a whole number there. It only makes sense that that answer needs to be a whole number. The question is how many people, and it doesn't make sense to say 25.7 people. So in the case that we had ended up with a decimal here, we would have rounded to the nearest whole person. In the B part, if this sample is representative of the adult population of the US, approximately 250 million, how many could be expected to cite friends as their greatest source of happiness? Well, if we were asked how many of the sample cited friends as their greatest source of happiness, then we'd be finding this 11% of 12,500. But we're not trying to find the number of people in the sample, we're trying to find the number of people in the population. So I need to multiply that 11%, or 0.11, times 250 million. And 0.11 times 250 million is 275. That answer doesn't make sense. I don't think the calculator took my decimal on the 0.11. Actually, I think my calculator battery's about to die. 0.11 times 250 million gives me 27,500. That's a much more reasonable answer. 27,000. No, I'm sorry, I'm not reading that correctly. 27,500,000. 27,500,000. That makes sense because 10% of 25 million would be 25. 10% of 250 million would be 25 million. This is just a little over 25 million.